So essentially we have 1 hour and a half. So let's present in about 40 minutes, leave 5 minutes for questions, and people can ask clarifying questions as we go along. If that's okay with you guys. Okay, and Ricardo, welcome too.
Hi, Ricardo.
Ricardo.
You're mute.
João Vitor, how much time do we have, each one?
Yeah, try to present in 40 minutes and leave 5 minutes for questions, okay?
Okay, that's perfect.
So, who is first here? Victor is first.
All right.
Please go up.
Let me share my screen.
Yes.
This one. All right. All right, now it's better for me to see like that. All right. So first of all, thank you all for coming. I'd like to thank SBE for organizing this conference. I'm really happy to be here with you guys. Not exactly here, but virtually here. And today I'll talk about my paper called Identifying Marginal Treatment Effects in the Presence of Sample Selection. The paper was co-authored with Otávio Bartalotti and Desiree Kedani from Iowa State University. And in it, we are facing two challenges. Our problem has endogenous self-selection to treatment and endogenous sample selection. And our identification strategy addresses both problems at the same time. In order to tackle the first problem, we focus on the marginal treatment effect, known here as MTE. And in order to tackle the second problem, we offer a partial identification strategy that will provide bounds that are uniformly sharp around the treatment parameter. I will explain later on what I mean by uniformly sharp. And by later on, it's really later on. But so far, I'd like to point out that those bounds have this nice property. And our theoretical framework matches multiple applications across economics. And today, we will focus mostly on our running example. So let's say that we are trying to estimate the effect of a job training program on wages. If time permits, and I don't think it will permit, I will also talk about my empirical illustration, where we analyze the impact of insurance choice on health expenditures. So let's use our running example in order to understand our setup and our target parameter. So basically, we have an instrument Z. This instrument has to be continuous. So let's assume that this training program has some sort of random allowance that is given to each participant. Finally, we have our treatment. We want to estimate the effect of this treatment, and we denote treatment by D, and it's a job training program. So you can think it about, in the US, the Job Corps training program, or in Brazil, you can think about Pronatec or Jovem Aprendiz. And people can choose to enroll in this program, and we model this choice using a single threshold crossing model. So basically here, we have P as our propensity score, and V is the latent heterogeneity variable. It's the resistance to the treatment. So larger values of V make it harder for the person to actually take the treatment. Moreover, we have two pairs of potential outcomes. We have potential employment that we denote by S0 and S1, and we also have potential wages that we denote by Y*0 and Y*1. However, we only observe wages if the person is actually employed. And as a consequence, we have our second endogeneity problem. That is, there is sample selection in our problem. In order to address both problems, we have a specific target parameter. Our target parameter is a function known as the marginal treatment effect on wages for the always employed population, and mathematically is given by this expression. It's a somewhat long expression. It's slightly unusual treatment parameter, so let's understand each part of it separately. So first of all, our outcome of interest is wages. So it is basically the censored outcome variable here. We can see the y star variables in the expectation. In order to address selection to treatment, we condition on the margin on the latent heterogeneity variable v. In some sense, v works as a control function. Moreover, in order to address sample selection, we condition on the always employed subpopulation. So basically, our parameter is focused on a population whose S0 equals 1 and whose S1 also equals 1. So this person here is employed regardless of their treatment status. Finally, as a consequence of this choice, this parameter is capturing the intensive margin of the effect. If you are interested in the extensive margin, you could analyze the effect of wages either directly on employment or on labor earnings. But if you actually want to analyze the impact on productivity, that's an important parameter if that's your goal. So are there any questions so far? I will proceed. So for today, I will focus on the first 3 sessions of the presentation. I'll talk about the context of our paper. I will explain our model, and then I will have a deeper explanation about our partial unification strategy. And I will briefly talk about summation, and then I will conclude. If someone is interested in our empirical illustration, I have slides for that after the talk. So let's understand the context of our paper. In this paper, we identify the MT function under 4 sets of assumptions. First of all, we do not restrict sample selection at all. So it's a very flexible mechanism for sample selection. And those assumptions will be enough to partially identify the MT function. However, the bounds around the MT function with an unrestricted sample selection mechanism can be very wide, and are likely to be wide. So we offer additional assumptions that will tighten the bounds around the MT function. So the first assumption that we add is the monotonicity in selection assumption. So we assume that S1 is greater than or equal to S0. Then, if we want to tighten the bounds even further, we can use a stochastic dominance assumption that we'll explain in detail later on. And finally, if you want a pointed identification result, you can impose that there's no selection effect in the problem. And the advantage of deriving uniformly sharp bounds on the MTE is that as a consequence of this uniformity, we can have sharp bounds around any parameter that can be written as a weighted integral of the MT function. So, and the most famous parameters in the treatment effects literature can indeed be written as weighted integrals of the MT function. And as our contribution, I would like to highlight 3 points of our paper. So first, we only require an instrument for treatment choice. We believe this is important for the applied researcher, because especially in labor economics, it's very hard to find an instrument for sample selection. Basically, finding something that is excludable from wages when you're analyzing employment seems quite hard to find. Moreover, our selection mechanism is very flexible. It allows for correlation between the treatment choice and the effect on employment and on wages. And finally, we are the first paper to focus on the MT function as our target parameter. If you guys want, I do have slides for the literature review, but I don't think it would be the most useful for us given the time constraints. So let's talk about that later on. So now let's understand our model in more detail. So here I have a notation slide. You can see the general framework on the middle column, and on the right-hand side, you can see everything translated to our running example. Importantly, beyond the notation I have already explained it, I would like to point the second to last line, where we can see that I define labor earnings as a Y variable. So it's basically sample selection times the Y star variable. As a consequence of sample selection, we can define 4 latent groups. So basically, those latent groups are defined by the pair S0 and S1. And today, we'll focus on the first group here. We focus on the always observed group. That is, people who are in our sample regardless of their treatment status. And our identification assumptions will basically constrain those latent groups in specific ways, allowing us to extract more information from the data. Whenever you see observed in this talk, you can also think about a person being employed in our running example. So as I mentioned, we use a generalized Roy model for treatment choice. Importantly, this model imposes monotonicity. We have similar restrictions as the ones imposed by Imbens and Engrist when they are analyzing the late parameter. And we normalize V here to be uniformly distributed, the standard uniform. So now let's understand our assumptions that will allow us to identify the MT function. The first 4 assumptions are sufficient for partial identification, and they are similar to the traditional assumptions in the MT literature. However, since we also have sample selection in our framework, we have to add a few bits to the usual assumptions. And let's cover those new things here. So we assume that the instrument Z is independent from all outcome variables and from the latent heterogeneity variable. We also assume that the propensity score is a continuous variable. That's important for us because we'll take derivatives with respect to the value of the propensity score. So we do need it to have a connected support. We also have to assume that there is a treatment group. So there is a positive mass for the treatment group. But we also have to impose that our subpopulation of interest has a positive mass for every value of the latent heterogeneity variable. Finally, we have to impose that some first moments are finite. The 4 assumptions I just showed are sufficient for identification, but they may provide us with quite wide bounds. In order to tighten those bounds around the MT function, we propose the monotone sample selection assumption. Basically, we are imposing that S1 is greater than or equal to S0. So basically, what we are doing here is, instead of having 4 latent subgroups, we are ruling out the existence of the second one. We are basically imposing that the group that is observed only when untreated do not exist. So we are left with only 3 subgroups here. If you want, in our running example, it basically means that training can only move people into employment. It can never move people out of employment. That is a restriction in the empirical context. It's basically saying that the reservation wage is not increasing. The person still accepts to work under the same wage as before, but the person may have a better wage regardless of that. Finally, if you want to tighten the bounds even more, you can impose the stochastic dominance assumption that is given by this somewhat large and ugly inequality. So let's understand what this assumption is actually imposing. So first, it is a stochastic dominance assumption. So we are comparing 2 CDFs. And the 2 CDFs that we are comparing are the CDFs related to the treated wages for 2 subpopulations. In blue, we have the always employed population, and in red, we have the employed only when treated population. And we are basically saying that the blue population has better wages than the red population. In our empirical example, it's basically saying that there is a positive correlation between potential employment and wages. So people who have better employment outcomes will also have better wages in a stochastic sense. Finally, if you really want to get point identification results, you can impose that S0 is equal to S1, in terms of our latent groups, it's basically focusing on the two middle groups and ruling them out, saying that they do not exist. So we are left only with the always observed population and the never observed population. Are there any questions about our assumptions? All right, let's proceed. So now we reached the main part of our talk. We will discuss identification. However, this talk is not about point identification. It's only about partial identification. We will not observe the full picture here, but we will have bounds around the MT parameter. So let's recall our target parameter. It's a function. And since the expected value is linear, we can break it in two parts. And I will discuss identification of each part separately. In order to do so, we have two building blocks. The first building block is related to point identification of the joint distribution of y star and s given v. After point identifying this object, we will focus on the conditional distribution of y star given that the person is employed and its value of v. And we will show that this conditional distribution can be written as a mixture of latent groups. And this mixture result will basically contain all the intuition behind our identification results for each set of assumptions. And here we will discuss all sets of assumptions and how the bounds change from one set to the other. So let's start with our building blocks. In the first building block, we are trying to point identify the joint distribution of wages and employment given V under assumptions 1 through 4. So under our most flexible set of assumptions. So we start with this equation. This equation is a key equation in the MIT literature. I will not discuss it in detail, but basically, if we take derivatives, we have on the left-hand side exactly the object that we want to identify. And in the right-hand side, we have an object that is based entirely on observable variables. So here, I'm basically showing that it is possible to point identify this interesting distribution. Moreover, we can also identify the marginal distribution of employment, also using a derivative. And combining those two results, we can identify the conditional distribution of wages given employment and V using a ratio of derivatives. We have the same kind of results for the untreated state. Here we are just changing the value of D. And now that we have point identified the conditional distribution of wages given employment and V, we can discuss how this distribution can be written as a mixture of latent groups. So basically, the conditioning set is the observed treated group. The observed treated group is composed only of two types. There's the always observed group in blue, and the observed only when treated group that I denote in red. And at this point in time, I will assume that I know the proportion of those two groups within the observed treated group. And I denote this proportion by alpha. As a consequence of this decomposition, we can write the conditional distribution of wages given employment as a mixture using basically the law of the rate expectations. We can write it as a mixture of those two subpopulations. And the mixture weights are given by this proportion alpha p, where alpha p is the proportion of the always observed population within the group that is observed when treated. And as a consequence of this result for the CDF, we have a very similar result for the expected value. And let's understand why this mixture result is so important for us. Basically, we know the distribution in black. We know the distribution of wages given employment. And we know that the group we care about has a mass equal to alpha. And this mass of people can be anywhere within the distribution in black. It could be equally spread around the distribution. It could be located slightly to the right. But in a worst case scenario, it would be located entirely to the left of the distribution. The population we care about, the always employed population, might have the worst wages within the group that is employed when treated. In this worst case scenario, we can derive a lower bound for the CDF of the always employed group using a trimming distribution. So basically, we take the point identified distribution in black, and we discard its right tail. And as a consequence, we have a lower bound for distribution, and under assumptions 1 through 4, we have a lower bound for the expected value that we care about. And this lower bound is basically a trimmed mean where we discard the trimming proportion is equal to alpha. For the upper bound, we have a very similar reasoning. But instead of focusing on the left tail of the distribution, we actually focus on the right tail of the distribution. For the upper bound, we assume that the population that is always employed has the best wages within the population that is employed when treated. As a consequence, in this best case scenario, we can have an upper bound that's basically discarding the left tail of the distribution. And given that the upper bound of the distribution is given by this trimmed proportion, this trimmed distribution, the expected value, the upper bound for the expected value will also be a trimmed mean. But now we are discarding the right tail of the distribution. A very similar result holds for the untreated state. But now, instead of the trimmed distribution is not alpha anymore, is now denoted by beta, where beta is the proportion of the always employed population within the population that is observed when untreated. But it's the same kind of reasoning. We have best case scenarios, worst case scenarios, and we discard either the best wages or the worst wages. And as a consequence, we can combine those two results and derive bounds around the MTE, once more using best case scenarios and worst case scenarios. Are there any questions so far? One question that I was hoping someone would ask is, there is actually a problem here. Those bounds depend on alpha and beta, and I have assumed that we know that out of nowhere. We're God and we know it. But that's just so far. We can say more stuff about the alpha and beta, and that's our focus now. So basically, alpha and beta, they depend on the joint distribution of S0 and S1. However, we only know, or at least we can identify the marginal distributions of S0 and S1. Can we say anything about the joint based on the marginal distributions? The answer is actually yes, we can. There's an old result by Bull and Frachet that shows that the joint is sharply bound by this expression. The joint distribution is sharply bound by this expression. Combining this classical result in the stats literature, actually in the probability literature, with our previous identification results, we can partially identify the joint distribution of potential employment statuses using the result in this slide. Combining this with our previous mixture results, we can bound alpha and beta, and we can derive bounds for all possible values of alpha and beta. We can pick the smallest potential value for the lower bound, and we denote that by delta underline as a function of p. And we can also pick the largest possible value for the upper bound that we denote by delta bar as a function of p. And as a consequence, we have our first proposition here. So we have already derived that the MTE function lies within those functional bounds. But the interesting part is that the bounds are uniformly sharp. It is completely unfeasible to prove that the bounds are uniformly sharp in a short presentation, but now I will actually define what is uniformly sharp. And the definition was actually given by Sergio and his co-author Reader in 2019. And the definition is the following one. For any function within those functional bounds, I can create candidate random variables denoted by tilde values that satisfy three properties. First of all, the tilde variables will respect all the imposed assumptions, all assumptions 1, 2, 3, and 4. Moreover, those tilde variables, those candidate latent variables, will induce the joint distribution of the data. So when I apply the generalized Roy model to those latent variables, I will basically recreate the same distribution of the data. So I cannot disentangle all those DGPs could be possibly creating my data. But importantly, those DGPs will achieve the candidate target parameter. So I can actually show that any function within my bounds is attainable. And that's the definition of uniformly sharp. Is that clear?
Possible.
Sure.
I have a question. So it's actually about like something you said before. So just to see if I'm getting, these bounds are going to depend on two things, like the functional bounds and the bounds you got from the Boole-Frechet theorem, right? Like it's a composition of both. Like
yes, I do use the Boole-Frechet bounds in order to bound the trimming proportions. So the bounds around the function depend around the target parameter. They depend on a trimming proportion. And the trimming proportion at this point in time is also partially identified. So I have two bounds being combined here.
Okay, thanks.
No worries. Thank you for the question. And that's actually a great question because it combines very neatly with assumption 5. So now, if we want to tighten the bounds I have previously shown, we can impose the monotonicity assumption. And imposing that S1 is greater than or equal to S0 is interesting because now alpha and beta are point identified. Basically because now the observed when untreated group is composed only of the always observed group. And as a consequence, alpha is point identified by this ratio and beta is exactly equal to 1. Given that I do not need to bound the trimming proportions anymore, I can shrink the bounds around the MTE. And importantly for us is that 1 bit of our target parameter is actually point identified. The expected value of the untreated wage for the always observed population is actually point identified now. And as a consequence, the bounds become much simpler. Now we still have trimmed means, but one part of our bounds is point identified. And moreover, the bounds under assumptions 1 through 5 are once more uniformly sharp, following the same definition as before. Given that we have spent 30 minutes so far, we can definitely cover the bounds under assumptions 1 through 6 and with assumption 7 too. So let's proceed to our discussion about partialification. And one thing that I love about partialification is exactly this layered discussion. We can start with very flexible assumptions that are very credible and impose stronger assumptions in order to get more information from our data. And I do believe that such a layered analysis is useful when providing policy advice. So our sixth assumption is basically the stochastic dominance assumption that imposes that the treated wages for the always observed group are better than the treated wages for the group that is observed only when treated. As a consequence of this assumption, we have that one part of our target parameter, here in black in the first bullet point, is actually larger than or equal to this red object. And this red object is actually point identified. As a consequence, there's no need to trim the lower bound. And we can increase the lower bound without changing the upper bound. And then our bounds around the MT function are given by those inequalities here. The lower bound is entirely point identified, but is just like simple means, simple expected values, but the upper bound is actually contains a trimmed proportion. So the upper bound will be somewhat larger in a more informal sense. And again, those bounds around the MT function are uniformly sharp according to the previous definition. Finally, if you really want to say that you point identify your effects, you can impose that S0 is equal to S1. As a consequence, the sample that you observe only contains people who are always observed. And it's very easy to point identify the MT function in this case. And basically, you can use the classical results by Heckman and Viculasil in order to point identify this distribution. Are there any questions so far? All right. I will very briefly talk about, I will first talk about my extension results. One thing that is important for the applied researcher is that finding a continuous instrument is very hard. So we also have results for discrete multi-valued instruments. In this case, we have late parameters. So we have the effect on compliers, and we are able to derive uniformly sharp bounds for any late parameter. So basically, when Z is multi-valued, let's say Z can be equal to 0, 1, or 2, you can define 3 different lates. You can define the late associated with compliers from 0 to 1, the late associated with compliers from 1 to 2, and the late associated to compliers from 0 to 2. And we can actually derive uniformly sharp bounds around all those lates. And this uniformity is important because by bounding the 2 short lates, so the late from 0 to 1 and the late from 1 to 2, we can weight them to derive bounds around the larger lates, the late from 0 to 2, and that combined bound will actually be tighter than a bound that focuses directly on the late from 0 to 2. So we can get tighter bounds by focusing on all the details of the problem. Finally, I do know that some people like quantile treatment effects. I'm one of them. Sergio, I'm sure, is another one. So we also analyze the distributional marginal treatment effect parameter. So now we are trying to bound 2 CDFs, and we are taking the difference between those CDFs. And we can derive uniformly sharp bounds around those objects. And as a consequence, we can use our framework to also bound the quantile marginal treatment effect. Finally, let's talk very briefly about our estimation method. All the identification results I have shown are very simple because they are functions of observable variables. So our estimation procedure is basically taking sample analogs of those functions. One challenge here is that one of the objects in those functions is the propensity score, and we do have to estimate the propensity score. To do so, the easiest thing to do is to use a parametric linear probability model or a logit or a probit. You could estimate the propensity score non-parametrically, we don't do that in our Monte Carlo nor in our empirical illustration, basically because that would be a very slow process. But it is possible to use non-parametric methods here. Then we do have to estimate derivatives. That's slightly harder than estimating level of functions, but there are known ways to estimate derivatives. More recently, Kaloniko, Cataneo, and their co-authors have proposed an estimator, and they have a Stata package and a R package. So it's very easy to implement their estimation procedure. And this part is non-parametric.
5 minutes if you want questions. You still have 5 minutes and then questions, okay?
Sure. I think I'll try to have 10 minutes of questions, just to have a more engaging discussion. Finally, in our Monte Carlo, we do have a Monte Carlo exercise. It seems to work. I'm saying it seems to work because it does require quite a large sample, and the variance of our estimators is large, but it has correct coverage and all the nice properties that you want. There are a few drawbacks. First, we do not derive formal asymptotic theory for our estimators. Actually, even the standard MTE estimators, they do not have a formal asymptotic theory so far. There's a recent working paper by Yuya Sasaki discussing that. But most applied work relies on Robson's semi-parametric estimator. But Robson's only derived asymptotic theory for the parametric part of the model, and MTE relies on the non-parametric part of their model. So it's still an open question. And we want to analyze that further on in the future. Moreover, the estimation procedure that we propose in our paper assume that the covariates are discrete. So you can basically use subsamples in order to condition covariates. But if you want to consider continuous covariates, it's very hard. We don't have a good way to do that. We are postponing that for future work too. Just to have more time for questions, I will jump to the conclusion. And the conclusion is basically highlighting the main points of our paper. First of all, we identified the MT function with sample selection. We believe this is an interesting result, theoretically and empirically, basically because the MT function is a very neat object to discuss heterogeneity in a very formal and coherent way. Moreover, we have this layered analysis that allow us to understand the MT function, first of all, in a very unrestricted and credible way, and then we impose stronger and stronger assumptions to tighten those bounds. Our insight is basically that we can write the conditional distribution of wages given employment and the latent heterogeneity variable as a mixture. And this mixture provides a lot of information about the target parameter. So I'd like to thank you all for coming. And if you have questions, feel free to ask them. That's the best part of a seminar.
Yes, please. So now it's open for questions. And to be fair with the procedure here, Firpo cannot ask any questions, okay? And the same rule is going to apply when Firpo presents, of course. Sure. So let's hear from the audience.
Hi, Vitor.
Hi. How's it going, Ricardo?
Hi. Hi. Very interesting paper. Thank you very much for presenting us. I have just a few questions. So the first one is, I mean, in what kind you mean uniformly sharp? Does that mean that the integral with those bounds gives you bounds on the integral as well? I mean, I didn't get that part. What do you call by uniform in sharp?
Sure, that's quite important. So basically, I'd say the best way to distinguish that would be thinking about what I would mean by pointwise sharp. So the MT is a function, and I could derive, I have bounds for each point in that function. A pointwise sharp bound would fix a value of the latent heterogeneity and a value of the bound around that point of the function. And I would create candidate random variables that would achieve the target parameter, the candidate target parameter for that point, ignoring all the other points in the function. A uniformly sharp bound does that for the entire function at the same time. So now, instead of focusing on one point of the function, I define as my candidate target a function within my bounds. And I can find candidate random variables that will achieve that entire function.
It's like I create an envelope around the function.
Exactly.
But
so you, sure.
Okay, no, I mean, I'm just saying like, so, I mean, I'm just thinking like whenever you have an envelope in a function, let's say that you have a function and then you have another function that has, I don't know, a fixed length interval around the whole function. That new function doesn't make this function integrable, right? In general. I was thinking like, let's say, take a, I don't know, think about like a Gaussian density, let's say, okay?
Yes.
And make a band around the Gaussian density of a fixed length. Right? A Gaussian density integrates to 1, but once you put a bound on it, it doesn't integrate to anything anymore because it diverges. That's what I'm trying to understand. In what sense this envelope?
Sure. So my answer to your question is in order to estimate the bounds, we do rely on estimators that will impose that even the bounds are per se differentiable and the derivatives are continuous. So it will be a smooth function by assumption if you want to estimate them. So even the bounds will be integrable and you can take those integrals.
Okay.
But that's a good point. That's an implicit assumption.
So you're assuming that's going to be integrable after you apply the bounds?
Yes, I am.
Okay, I got it. No, I understand.
But that's a great question, and we should be explicit about it.
Yeah. I mean, yeah, because I have this problem once, and I was kind of, I mean, completely different scenario, nothing to do with treatment effect, and I realized that it's not so simple to bound something that was originally integrable to obtain something that is integrable again. With bounds of this type that are like fixed in each point. That's why I was interested. What do you mean by uniformly sharp?
Our bounds are not a fixed length bound. Like they will be wider
areas,
at
right?
the borders of the support.
Okay, I got it. Thank you.
No worries, thank you. Any other question?
I was wondering for the applied researcher, what kind of questions or issues could you address with your techniques that couldn't have been addressed before with the previous ones?
Sure. So it depends on, like, I'd say there are two complementing literature for us. In one case, there's the literature that focus on the heterogeneity of the treatment effect when there's no sample selection. I'd say those the main authors in that literature would be Heckman and Vitlasil, and basically they identify and propose estimators for the MTE when there's no sample selection. So using their framework, you could, for example, identify the MTE of a training program on wages, or as they do with Carneiro, the MTE of attending college on wages. Sorry, not wages, labor earnings. What we do beyond their work is to identify the effect of, for example, attending college on wages instead of labor earnings. We believe this is important basically because as a policymaker, you may want to increase the agent's productivity instead of only moving people in and out of employment. So that would be the main point, our main contribution to this part of the literature. About the literature that considers sample selection and treatment selection at the same time, my favorite paper would be Chen and Flores. It's a JBS paper where they focus on the late parameter, which may not be policy relevant. By focusing on the MTE, we do require a continuous instrument, but we can use the MTE function to analyze any policy relevant treatment effect. So you can even discuss policies that were never implemented before. So that would be the useful thing for the applied researcher. Or at least I think it would be useful. The MTE is not as popular as I would like.
Okay, so thank you. We're out of time.
Thank you very much.
Please, Sergio, could you present now?
Okay, thank you, João Vitor, Ricardo, and organizers of SBE meeting. I'm gonna share my screen and let me answer. I don't know, can I answer to Ricardo's question, or that's unfair? Perhaps I could talk to Ricardo later. Let's talk later, Ricardo.
Okay, thank you.
About uniformly sharp bounds.
Thanks.
Okay, so okay, now I think you can see my screen. And so that's a paper jointly written with Antonio Galvão, and who's Brazilian and nutrition, probably most of you know him, and a couple of other co-authors that we were able to put this team together, each one with his or her own expertise, right? So Martina is a theorist. She's Polish and works at Polish Academic of Science. And Tom Parker is an econometrician that works in Canada. And Pedro is a Portuguese applied person who is at Imperial College. And this project is a long, now I think, 5 or more, 6 years perhaps, that started. And now we have a version, we're submitting and presenting. Last month I presented 4 times. Now that cost of traveling is much cheaper, it allowed me to present many other places. So this all came from interaction with Pedro, because he has read that paper that Vitor cited, previous version, paper he reader that we have on bounds on distribution of treatment effects, right? And I said that, well, if you start thinking on how to rank policy interventions depending on the distribution of treatment effects and not on the distribution of the potential outcomes. So if you start doing something opposite as what people typically do, which is to compare distribution of the potential outcome under the treatment and distribution of potential outcome without a treatment, right? And see, for example, if the first dominates somehow the other one, right? The first order, for example, right? That would be, if that's the case, then you would have a clear ranking of those policies, right? But the thing is that by just comparing those distributions, you miss an important thing, which is the identity of individuals. And identity here matters because some people will gain and some people will lose from those interventions. Okay, so how can we replicate what I mean, the same ideas in Atkinson's paper, like in the 70s, when he basically said, look, if I want to say that one policy is better than other, or that one distribution, income distribution, would unequivocally be better than another one, right? For any type of utility function that that agents could have, as long as they are increasing in income, for example, or consumption, if it's consumption, right? And right, it's basically increasing, right? So you can show that stochastic dominance, first order dominance would suffice, right? If you have some concave utility function, then second order would be enough, and so on. So this kind of thing to say, look, I don't know exactly how people behave. I don't know exactly how they value those outcomes. I don't know the utility function, but if the utility function has some characteristics that make sense, right? What can I say in terms of which policy should I implement? And that started our project, right? Because and then Martina jumped in because we needed to think about, well, what kind of value functions or utility functions you should take into account when you start talking about potential losses, right? People may lose from the interventions. Not everyone will gain, right? So should losses be treated differently from gains? And yes, there is a huge literature, right? Prospect theory, Kahneman, and Tversky, they all brought us this idea that people in an asymmetric way value losses differently from gains. So we use that framework to come up with a relationship between distribution of treatment effects or gains and losses in a way, right? And that would allow us to rank policy interventions. But we knew that testing these would be very challenging. So that's why I asked Antonio and Tom to jump in this project as well to provide the statistical inference component. So in a way, I'm the project manager of this paper, right? And I think we had a very good team of people with their own abilities and skills applying to this entire project. So let me tell let me motivate and say something about this project. Okay, so that's what I was saying, that, I mean, you can just compare those potential outcome distributions or the marginal outcome distributions, right? And that's, and then in that perspective, from that perspective, gains and losses are irrelevant. But just see the income distribution under a given policy, the income distribution under a different policy or no policy, and I compare them, and then we'll be able to rank the policy or the no policy, right? Or the policy A against policy B, just by looking at the distribution of potential outcomes. But that ignores gains and losses, right? And we know that, for example, Heckman and a bunch of co-authors, right, in a bunch of papers, they have been vocal about, look, we should look at individual treatment effects, right? Because individuals are affected in different ways by those policies. Some people will gain, some people will lose, right? When you just look at the final outcome distribution, like the final level or the distribution of the levels, right? We are missing this important part, which is, well, those people, they departed, right, from a given initial point or something that could be thought as a counterfactor, which would happen to them if they did not get the treatment, right? And they arrive at a different value, right? So this change, or that could be a gain or a loss, is relevant from an individual perspective. So if you want to rank policy interventions, take into account what is relevant for the individual, gains and losses should be fundamental. Okay, so that's what we do here, right? And that's the important thing, that when you start talking about losses and gains, right, we know that loss aversion is an important thing, right? So if I lose $1, that's different from gaining $1 in terms of the same absolute value of my, let's say, value function, right? If you're loss averse, right? So if individuals are typically loss averse, right, does it have an implication in terms of the welfare function that we think that could somehow aggregate those preferences, or those the way that people value gains and losses, right? And yes, it could be, right? We can construct a social welfare or social value function, as you call it, that is based on the principle that, let's say, the policymaker or the planner, social planner, has on how individuals value gains and losses. And if this policymaker believes that the individuals are loss averse, right, that may have impact on the type of policies being offered, right? They can anticipate, right, that people are loss averse, so they will never, for example, offer policies that could generate very large losses to an important number of people, right? Or even small losses. Small losses to a large number of people would be even something that, even if, I mean, ATE is positive, right? The average effect is positive. If you're unable to redistribute after that, right, it could be that those policies that generate average gains would not be offered. Okay. We can also think that that is, in a sense, right, that this is basically just endorsing some normative reasons, right? And not necessarily is not something that comes from the individual component. Let's say that's basically the society has agreed that we should do no harm to anyone, right? So if I develop a vaccine, for example, I would only provide those that do no harm, right? And that is a choice, a policy choice that may have had an important impact in terms of what has been offered to us nowadays in terms of having vaccines to COVID-19, right? But you can think of many other examples, right, of these, and here I list some of those examples, in which, from a normative perspective, those policies that avoid losses are preferred, right? So the idea here, from a more abstract point of view, is to think of two treatments or policies, right? And let's call them A and B, right? So the thing is, how can you rank which policy would be better for the population? Okay. So what we argue here is that if you incorporate changes, right, in the outcome that I'm looking at, say income. So if I'm looking at income changes, right, I would be ranking policies A and B according to a relationship between the distribution of individual treatment effects under A and the distribution of individual treatment effects under B. Okay. But how can we how can we do this? Well, the way that you do is by deriving a new stochastic dominance criterion that we call loss aversion sensitive dominance, right? Which takes into account that the value functions of individuals are in a way that the welfare function incorporates the idea that individuals would exhibit loss aversion, right? And by loss aversion, we capture or we use the main features, right, used in this prospective theory literature, right? And then we show that if the value functions exhibit this kind of, uh, of, of properties, right? Then we're going to have a one-to-one mapping between this relationship between distributions of changes and preference of the policymaker in terms of policy A and B in terms of their welfare being generated. Okay, exactly like in this old in 1970 literature initiated by Tony Atkinson on how to rank outcome distributions based on just a few features of utility functions. Okay. We also have a problem here, which is the kind of problem that Vito had in his paper, which relates to the fact that if you really treat this not as changes, right, which are observed, right, is something that happened to me tomorrow minus what happened to me today. That's the change between today and tomorrow. But if you think of those changes as distribution, as treatment effects, right, comparing two potential outcomes, what would have happened to me if I'm treated with what would have happened to me if I'm not treated, you cannot observe both at the same time. So a distribution of treatment effect will not be point identified. And so we use bounds on those distributions and derive, right, it's the same type of relationship that we have, but now using bounds. And we show that when you use bounds, you're going to have a sufficient condition, right, to show that if that sufficient condition holds, then we're going to have that policy A will be preferred over policy B, right? But we also have a necessary condition which is less stringent, and then it can also be verified from the data. Okay. We do later we apply some new inference methods that are not ours, right? But that's a more technical and recent literature in which for the kind of test statistics that we have, right, that's very discontinuous, very non-smooth, right? We have to rely on inference methods that will allow us to do correct statistical inference, basically to construct confidence intervals, right, and test a null hypothesis using this tool. Okay. And then we have an application. I hope that I have some time to present the application. João, how much time do I have? Just to, because I don't know when I started.
Well, you have about half an hour, but if you want questions, 25 minutes.
Okay.
A little bit less.
Okay, good.
23 minutes.
Okay, 20 minutes. I'll try to finish in 20 minutes. Let's see. Okay, thanks. Okay, so I was saying that this has a long tradition in this type of welfare literature, right? But also some people have tried to establish, to test for stochastic dominance, right? Statistically. So Linton has a bunch of papers on this, right? That's set here, right? What we do, we are adding this new criterion to this to this to those other tests, right? It's somehow related to this optimal treatment choice literature. Not really. We are doing so many things in this paper that's difficult to say to which literature or brand of literature this thing applies to. But we are also using or applying this literature that, for example, André Santos has worked recently, Azim, Shaikh as well, right? That's basically an application of directional differentiable test statistics, okay? And if I have time, we're going to talk about that. Okay, let me let me establish the type of problem that we have, okay? Let's say that X is the change, okay? X is the change or the treatment effect, right? It's distributed according to F. That is in this set of admissible CDFs, right? And with bounded support calligraphic X, right? The bounded support is helps us a little bit, even though it's not something that is crucial. Let's say that the welfare function, right, is a function of the CDF of X, right? So it's basically the welfare function here is a very simplified one, right? If you think of what you're doing here, it's kind of, let me focus on one part of what is important here, right? We know that the welfare function could be looking at also levels, right? Levels are also important, but let us just focus on one aspect of it, right? Which is the part that we believe it's crucial, but it's missing, right? Many applications, right? Which is the how changes are relevant, right? So we are looking at a welfare function that's basically a functional of the CDF of changes, and it's an integral of a type of valuation or a value function that people might have, or that the policymaker believes that people have, right? This V function, the value function, may not even be the correct way that people value gains and losses. But let's say that the policymaker believes this is so, okay? So, and what he's doing, he's integrating, right, over the distribution of gains, this value function. So the integration could be, think of aggregating all individual value functions in a way, or I'm just constructing this welfare function in a way that is an expectation, right, of this V, right? V is basically assigning weights, if you wish to think so, right, to this functional of the density. So that's basically a way to say all possible or distribution of changes, right? How can I create a summary statistic of that, right? And that's what we have. That's what we're going to say that's what the policymaker has in mind. Okay. Okay. So this, we're going to call it the social value function, right? This way, as I said, this V need not to be any agent value function, right? But that's just a way to convert outcomes or changes, right, into a measure that can be compared. Okay. Now, F was the distribution or the CDF of gains or changes, right? Let's say that G are the marginal CDFs. So if you decide by policy A, then GA will be the income distribution under policy A, and GB will be the income distribution under policy B if you decide by B, right? So those are level or distributions of the levels, okay? So if you apply Atkinson's theorem, right? So he showed that for all increasing V functions, right? This criterion here, right? This expected, in that case, utility function, right? Or the expected value function, right? Will be greater for under GA than under GB, so you prefer GA, right? If and only if you show that GA dominates the first order GB. So you can go directly, you don't need to look at the individuals, you can go directly to distributions, and if you establish that GA dominates GB, you know that someone you prefer policy A over policy B, in the case that we're looking at levels, okay? Okay, that's not what you're doing. You're basically saying that, let's say that ZA is a variable that is distributed under GA, and ZB is a variable that's distributed under GB. So those are the potential outcomes of receiving treatment A and potential outcome of receiving treatment B. So instead of looking at ZA and ZB in levels, we are subtracting the initial value, or what would have happened to individuals, right, in the absence of treatment. That's Z0, okay? And Z0 is not a constant. Z0 is a random variable that would depend on observable characteristics that individuals have, and also on unobservable characteristics, right? And each individual would have a different value of Z0, right? So there is not a constant reference value, right? This can be thought in the prospect theory literature as having a random reference value, and that what makes this even more interesting. Okay, so and you're basically saying, look, following this tradition initiated by Hackman, one should look at treatment effects, gains and losses, right? For each individual to rank policy interventions. You do not be enough, or it masks a lot to look at levels, right? When you could have look at the changes and how much people gained and lost, not necessarily the distribution of those things here, because you know that there might not be any type of ranking invariance, right? People under no policy, right? When you implement policy A, someone who would be very well under distribution of Z0, right? Might be in a very bad situation under distribution of ZA, right? Or ZB, right? So there is no reason to believe that they would remain at the same ranking or the same or this. I mean, we don't know the dependency structure between ZA and Z0. That's the thing. Okay. If we knew, then we could have our W, our social value function, using also the joint of those things, which we don't. Okay. So basically, the type of things that we're going to assume for the V functions, those value functions, are that, well, they assign negative value to losses and positive value to gains. Value function is increasing, and there is an asymmetry in gains and losses, right? And we can rewrite that in this way, 1, 2, and 3. Okay, so this utility of losses and utility of gains, it's going to be non-decreasing and loss aversion. Okay, so as I said, XA is ZA minus Z0, XB is ZB minus Z0, and those are, they follow FA and FB distributions. Okay, so what would be one possible image, right, or one possible phase for this B function would be something like that, right? And that's, we are just getting this from Tvest and Kahneman, right? That's the kind of thing that we have in mind, okay? It could be, we're not explicitly saying that it has to be convex for the locks and concave for the gains, right? Even though those assumptions allow this, it could be just concave, right? But if you think in a I mean, like using some kind of a second order, right? When you are looking second order, or you start looking at a second derivative, actually, right? You can think of this as well as being a good representation of what they have in mind. Okay, but you're not using that necessarily. The only thing that you're using are those three assumptions that I described. Okay, so we're going to define what we mean by loss averse sensitive dominance, right? We're going to call, let's say, we're going to say that FA dominates FB under this criterion, right? If this thing happens, okay? FA will dominate FB, right? If, for example, you have two equivalent criterions, so if and only if this happens, and I think this one here is easier to look at. So this first one is basically saying that for the negative part of the support, FA has to dominate FB first order, right? Usual, ordinary first order dominance criterion, but only for the negative part of the support. The second condition, after rewriting it and putting together, basically establishes the following. Okay, this has to be smaller than 0, right? Okay, but it also has to be, when you come from this part to this, right, is smaller than this. Okay, what does this mean? Okay, well, this means that we may have, right, suppose that this is smaller than 0. Okay, we may have that for the positive part of the support, FB actually dominates FA, right, in first order. That's fine, as long as this is not larger, the dominance part is not, the dominance criterion is not larger than what happens in the negative part. Remember, people are loss averse, so losses have to be more important than gains, and that's what we have here. So that's basically the new criterion. So basically, we are looking now, this has to be smaller than 0 as well. So basically, we're saying that this has to happen, and this has to happen, and this has to be smaller than 0. So basically, we are here in a situation in which we combine those two conditions here, and that looks like a lot first order stochastic dominance, but with this twist that you have to treat separately the positive and the negative parts of the support, and we have to have this extra condition in which what happens in the positive part cannot be larger in creating those differences in what happens in the negative part. Okay, but those things are testable. That's the interesting thing. Okay, if you have an empirical distribution of FA, empirical distribution of FB, you can test this, right, for all x, right? Some type of homograph mean of tested statistics would allow us to do this, right? And that's exactly what we do. Okay, and then there are some interesting features here, right, which has to do with the fact that unlike first order stochastic dominance, right, if you say that the means are the same in the first order, necessarily they have to have the same distribution, right? If one dominates the other one, it only happens when they are identical distributions, and this is not the case for LASD. So it could be very well that treatment A has a larger AT, or so this is an implication. So let me put this way. So FA dominates FB, right? This implies that this average treatment effect would be greater, not smaller than, right? But it could also be the case that they have the same AT. So if you have two policy interventions that produce the same AT, right? We can still untie and see which one would be preferred by using this criterion. that's something that you couldn't do with first order stochastic analysis, right? Another important situation that you have is this status quo distribution, which is basically when you don't do anything. It's basically a degenerate distribution at zero of the gains and losses. And so that's, so I have to run because I don't have much time. So that's a situation in which first order and loss aversion, they are equivalent. One of the comparisons is using status quo. This is just to visualize how those things are different, right? So Z naught is distributed according to 0, 1, 2, and 3, right? Uniformly, and ZA 3, 2, 1, 3, 2, 0, 1. So when you take the difference, right, it's going to be 3, 1, minus 2, minus 2. Right? So we have a distribution for XA. If you have the polis doing nothing, status quo would be just generated at 0, right? Even though ZA and ZB, they have the same distribution, right? There's nothing you can think of ranking ZA and ZB according to this LASD. Just an example. Let me jump.
Minutes. You have 5 minutes and then 5 minutes for questions.
Okay, we'll finish in 5 minutes. Let me just say that life gets a little bit more complicated if you do not think of changes. So FA and FB are not point identified any longer, and they are set identified. So those are CDFs. How can I bound those CDFs? Well, those are CDFs of effects, and we know how to do that, right? That's in several papers by Yang Fan, and I also have contributed to that. And those are basically bounds based on Makarov, right? Who first came with the idea of bounding sums of random variables that you know the marginal distributions, but you don't know the dependent structure, you don't know the joint. So we're going to have U and L as lower and upper bounds for this F, which is the distribution of the treatment effect. Those are the formulas. They depend on the distributions, right, of the marginal potential outcomes, right, which is Z naught, Z A, and Z B here, right? We come up with those. And then this is just an example of the type of CDFs. So each one of those here are, I mean, you know the marginals. The marginals are the same, just normal, standard normals, right? The blue is the upper bound of the Makarov. The red is the lower. And here possible treatment effect distributions depending on some structure that you put on the joint. Okay, so we have some results as well here. We have a result that it's a sufficient statistic or a sufficient condition for testing that comes from the fact that if you look at the most to the left, right, so totally dominated distribution, right, of A, and most to the right distribution of B, right, if this thing here happens, even if the most of the worst case scenario, right, then that's going to be a sufficient condition for A to dominate B. This is a necessary condition, right, in which we invert those U's and L's. I'm not spending much time here. Let's say that all of those are testable things. So the econometrics component is basically say, let's assume that have empirical distributions, right, for X's in the first time, right, and that we can observe, right, the gains and losses, and then let's say that you cannot, then you have to use bounds, right? So have two scenarios, and we apply those two scenarios to our tested statistics, right? And you construct them by following something that was shown before when we're defining LASD, right? You can construct those functionals this way, right? And one way to detect whether a null hypothesis that A dominates B is by looking at what happens to this T function here, right? If it's positive, then it's a violation of the null, and you can test for those T1 and T2 being positive. That's basically what we do, right? Instead of looking at directly what we do, right? We construct testing statistics based on those functionals, right? Which is one that is, let's say, has a Kolmogorov mean of flavor, right? It's a soup, right? And another one which is more of this Kramer-Mises type test statistics. Then we show, right, using this directional derivative literature, we show that we can use bootstrap to come up with correct confidence intervals and do inference for those testing statistics. Okay, so I'm gonna jump all of those and go directly to an application that you have, right? I have many slides here, right? An application was basically using this paper by Bittler, Hoynes, and Gelbach, that was published in AR in 2006, which they are comparing to, but yeah, I mean, just once, 30 seconds. Okay. And we apply that, we use that empirical application to our case, right? And what you had in mind is, okay, can you test which one would be preferred, which jobs first, or this AFDC, which was the initial thing. And you show that we can test using those two criteria, right? Criteria, LASD and FOSD, and you get different results that could be seen here, that we would reject the null, that this JF dominates AFDC here, but you'll not be able to reject using FOSD. So this is the paper, right? So what we did was to provide, to incorporate loss aversion to rank social policies, right? So we see that this is different when we incorporate loss aversion. That produces a ranking type of distributions that's different from first order stochastic dominance. We apply to both cases, point identified and partially identified, right? And we show that you can do inference based on resampling techniques. That's the paper. Thank you, and sorry for taking too long.
Okay, so thank you, Sergio. So we have time for questions now, please. So, Sergio, I have a question.
Go ahead.
The P-naught, I understand in some cases it's obviously a random variable, but you know, to my mind, I thought about the training program for people that are employed and have income, right? Or have a wage. So of course, from the beginning of time, you know exactly what the salary of the person was. So you could condition on that, right? At least. So what kind of examples would violate that, and that would, you couldn't really treat the Z-naught as a predetermined variable?
Well, that's a good point. So I think that we can condition on the value of Z-naught, right? And that would be the way that you're not doing this, but we can easily do everything conditional on Z-naught, right? But the way that we interpret this in this treatment effect literature is that Z-naught is not necessarily the initial value, is what would have happened to you in the case you do not get the program after the program has initiated, right? It's not necessarily something that happened before, something that should be happening now, but the thing is that because we didn't get the program, I'm not observing. So if there is any time component that's random so that heterogeneous to different people, that would make this Z-naught different from what you observed in the past. That's the only difference. That's more of interpretation. So if you have this interpretation in mind that Z-naught is what happened in the past, so I don't have a partial identification problem. Everything's point identified. It's just change, time changes that I'm observing. That's the easiest way to proceed, actually.
Thank you. You are mute, Ricardo.
Okay, sorry, I have one question. So in the you do a bootstrap, right, for to get the critical values, right, of the test.
That's correct.
And and in the bootstrap, I mean, the validity of the bootstrap that you show, even under partial identification, that's also fine.
Yeah, exactly. We do. It took us a couple. I mean, that's why it's a long project that we initiated a long time ago. Yeah, it took us some work to show the validity of the bootstrap.
Okay, under the partial identification. Okay.
Even under the partial identification in 5 cases. Yeah.
Okay, and you use the fact that it's differentiable with respect to the CDF, right? Hadamard differentiable, and that's how you do the bootstrap strategy.
Yeah, this is directionally differentiable. We have to. It's like, I mean, it has this feature of, I mean, it's like doing. I mean, it's like, how do you do inference, right? When you have a test that's non-pivotal, right? That depends on the null that you're testing. It's the same type of thing that you have here, right? It's non-uniform, right? So it depends on your null hypothesis. So that's why you had to do something that's, I mean, not the usual thing to do. But I mean, the analogy would be, how do you deal with non-pivotal test statistics? But now applying not to a parameter testing, but to this functional testing.
The functional test, yes. I think it builds on the work of Santos, no? From
yeah, exactly.
Yes.
That's perfect. Yeah, one of the papers that I cited in the beginning. That's exactly that.
No, I know this. Okay, thank you.
Okay, for the interest of time, I think time is up. So we should thank the speakers, at least virtually.
Well done, guys.
Thank you very much, and thank you. Yeah.
Okay.
So
thank you very much, João and Ricardo. Yeah, and Victor, it was great to see you again.
It was great to see you again, Sergio. Thank you very much, João and Ricardo. Thank you all for coming. See you.
See you.
Okay.
Yeah, thank you all, guys.
Ricardo and I will stay here and talk a little bit.
Okay.
All right.
I'm gonna leave. Okay.